All right, everyone. Our homework over the weekend was worksheet number 6 and worksheet number 7, question 1 and 2. The answers are up on the board. Any issues with any of those questions on worksheet number 6 or 1 and 2 on worksheet number 7? Courtney? 4? All right. Colin? 7? Brenda? 3? Oh, worksheet number 7, question number, sorry, which one? Okay, let's take a look at number 1 then. Yeah. So we've got 3, 4, 7, and question number 1 on worksheet number 7. I think worksheet number 7, I think that both of those questions are pretty much the same, right? We just had different numbers and maybe different directions. But I think if you're probably okay to do one of them, you're probably okay to do the other one. Courtney, question? Well, let's take a look at question number 1, okay, and then I'll ask you to try question number 2 again. And, after we've gone over question number 1, if you still have trouble with it, then we'll go over worksheet number 7, question number 2 as well. But we'll give you another chance on it before we go over that one, okay? All right, 3, 4, 7, and we'll go worksheet number 7, question number 1. Number 3 on worksheet number 6, first of all. The question says, an electric force of 7.19 times 10 to the negative 8 newtons acts between two charges, both of magnitude 2.00 times 10 to the negative 10 coulombs. Calculate the distance between the two charges. We don't have the question up on the board here, so there's nothing we can circle in terms of givens or anything. We'll write down the givens in the old-fashioned way, in the way that a lot of you still do write down the givens, which is absolutely fine. We have a force here, a magnitude of the force of 7.19 times 10 to the negative 8 newtons. We have two charges, Q1, both of the same value, 2.00 times 10 to the negative 10 coulombs. And we're looking for the distance. So there's only one variable in that equation that we've got to solve for, but it is probably the toughest one to solve for. We're going to rearrange this equation to solve for r. The first thing we got to do is get it to the top. It's on the bottom right now. We don't want it on the bottom. We can't solve for it when it's on the bottom, so let's get it to the top. How are we going to get that r squared to the top? Cross multiply, right. It becomes f times r squared equals k q1 q2. Now we could have in one step just taken the f down as well, right? So it would have been r squared is equal to k q1 q2 over f. We're just swapping the r squared and the f. The r squared goes up by multiplying, the f goes down by dividing. As Colin said, we're cross multiplying, right? So far so good? Now how are we going to get this r? Now it's the easy part, right? Not going to square it, no. We're going to square root both sides, right? In order to get r on the left-hand side, you got to square root r squared. In order to do that on the left-hand side, we've got to do the same thing to the right-hand side. So it's going to be r is equal to the square root of k q1 q2 over f. So now I plug my numbers in. It's that constant, 8.99 times 10 to the 9. By the way, does anybody remember what the constant was for gravity? The gravitational constant? 6.67 times 10 to the minus 11. Okay, you don't have to have that number memorized. The point that I just wanted to remind you of here was that this is a much bigger constant than the constant for gravity, and that tells us that the electric force is much bigger than the gravitational force, right? 8.99 times 10 to the 9 times 2.00 times 10 to the negative 10. See what I just did there? Is that okay? I only did that because I ran out of space here when I'm writing, right? I could have written down, if I had space, 8.99 times 10 to the 9 times 2 times 10 to the minus 10 times 2 times 10 to the minus 10. But I ran out of space, so I put a little squared in there. Isn't that the same thing as saying 2 times 10 to the negative 10 times 2 times 10 to the negative 10? Yeah. That's fine. If you want to write it out, that's fine too. The force here is 7.19 times 10 to the minus 8 newtons. And we got to square root that. When we do the math on that one, should work out to be 7.07 times 10 to the negative 2 meters. Make sure you can get that, okay? Put that into your calculator. Make sure that you can get that. If you don't, then put up your hand and we'll help you with it. Yep.
So was like the second number just a typo then?
Uh,
I had it as
the charges there?
yeah.
Oh, you know what? I made that change on my paper, and I thought I had made it on your worksheet as well. It said both of magnitude 2.00 times 10 to the negative 10 newtons. Yeah, it should have said coulombs, sorry. If that's what threw you off on that one, guys, I'm sorry, that was my fault. It should have said coulombs as opposed to newtons. How many people caught that should have been a coulombs? Okay. Okay. Sorry. As I say, that was my fault. If that was your problem, then don't panic because you're good if that was your problem. I can promise you on a test, we won't have that problem. Okay? Your tests are old diploma exam questions, and they make those mistakes, but they fix them before they ever appear on a diploma exam because they have like 50 people proofreading it first. Okay? All right, so we're good with that one then. Number 4, I think, was the next one. Yep. Number 4, I really like this one. Two identical charges are separated by a distance of 1 meter. The repulsive force of 3.6 newtons acts between the charges. What's the magnitude of each of the charges? Now we've got a distance here that separates them of 1.00 meters. We've got a force of 3.60 newtons. We're dealing with numbers, at least, that aren't crazy exponents and negative exponents, so it makes it a little bit easier in that sense. We're looking for the charge. We're looking for the magnitude of both charges, in fact. But it tells us that the charges are both the same, right? They're identical charges. So we're looking for Q1 and Q2, but the reality is if we find one of the charges, we're good because they're both the same. The equation that we know applies here is that Coulomb's law equation, F is equal to K Q1 Q2 over R squared. But if they're both the same, both charges are exactly the same, they're identical, then let's just call them the same thing. Instead of calling them two separate things, Q1 and Q2, let's call them both the same thing. Call them both Q. Call them both whatever you want. I'm going to call them both Q. It becomes K times Q over R squared. Is that okay? Is that good? All right. We can simplify this a little bit. Not unlike we did in the last question, actually. K times Q is the same as K times Q squared over R squared. Now we have the value of F and K and R. The only thing we don't have here is Q. And we've got it together now, so we can find the value of Q. Let's take the R squared up by multiplying. F times R squared. Take the K down by dividing. How do we get Q by itself? We're going to square root it, right? How many people said here K times Q is K times 2Q? Okay, that's adding Q plus Q, right? When you multiply Q by Q, you're going to get Q squared. Does that make sense? Okay. So we're going to square root this now. Q is going to be equal to the square root of F times R squared over K. And now it's just a straight math question, right? Plug in your numbers. 3.6 times 1 squared divided by the constant. And the value that we get there is 2.00 times 10 to the minus 5. That's the charge of one of them, but since they're both identical, that's the charge on the other one as well. Is that good? How many people, again, got that question? Okay, good. If you got that question, that's excellent. That's a tough question. You kind of got to work your mind around. Now, after we've done it, if you ever saw something like that again, it's not so bad, right? You could quite easily repeat that, I think. But having not seen it on Friday, I think that's a pretty tough question. Go ahead. I'm sorry? No, you don't have to consider the plus or minus. No. Yeah, we do drop the sign of the charge when we plug it in, but we don't have anything with the sign of the charge in this, right? We've got a negative exponent, but we don't have a sign We're not saying this is plus 2 or minus. Right, right. Yeah, when you take the square root, it could be a plus or a minus, but in the end, we're not paying any attention to that. We're going to say the magnitude of the charge here, just the same as when we plug it in. The magnitude of the charge is positive 2.00 times 10 to the minus 5. It does tell us in question number 4 that it's a repulsive force. So we know that they're both the same, either both positive or both negative, but we don't know which it is. We don't know whether they're both positive or both negative. This equation won't tell us, okay? That makes sense? Okay, we need to go over number 7 here as well. 7. Oh, this is one of those ones where we're touching two objects together and then finding the force. We've got an initial charge of 2 coulombs. We'll call it charge number 1 of 2.00 coulombs. There's a second one of 6.00 coulombs. And there's a third one that is neutral, so it's 0 coulombs. It says the first charge is touched with the second one. When we touch 2 and 6 together, what are they going to balance out to be? What's the total charge between the two of those? The total charge between the two of those. Carson, what's the total charge between 1 and 2? Good. So the total charge after we touch them together is also going to be 8. When they touch each other, they're going to balance out. So it's going to have to balance out to be 4 and 4, right? And charge number 3 hasn't changed. It's still going to be 0 coulombs. It then says that the first one is then touched with a neutral object, the third charge. 4 plus 0 is 4. The total charge between the two of those is 4. We divide that by 2, and we're going to get 2 coulombs. And 2 coulombs. The second one is going to remain 4 coulombs. Does that make sense? How many people got that so far? 2, 4, and 2. Okay, good, good. Now we want to find the electric force that acts between the first charge and the second charge. So we're going to use the values of Q1 and Q2. It's 8.99 times 10 to the 9 times 2 coulombs times 4 coulombs. The third charge doesn't come into play here at all. If we were trying to find the force on the middle charge due to the other two, then it would come into play, but here we're not. We're just trying to find the force between 1 and 2 here. The distance that separates them, we're told in the question, is 5.00 times 10 to the minus 2. And we can't forget to square that. Probably the single biggest mistake, the single most common mistake in this type of question is forgetting to square that distance probably. When we do the math on that one, it works out to be 2.88 times 10 to the 13 newtons. This is a question, or a question like this, is a question that there's a decent chance will appear on a test or an exam. It's not one of those ones that I can say, oh yes, this will be there. But it's one of those ones that I can say, hey, look, we better make sure we understand this because there's a pretty good chance that it's going to appear. Hey, just out of curiosity, we weren't asked to find the acceleration in question number 7, but what if we were? What if I had have asked you to find the force and I had have asked you to find the acceleration? What would we have done? Make a note of this, okay? Nobody's raising their hands, so I assume that nobody knows the answer to that question. Make a note of this, please. If you're ever asked to find the acceleration in Physics 30, then find a force first, whether it's an electric force or a magnetic force or whatever force it is. Find that force and then divide it by mass. Newton's second law, right? F is equal to m times a. You want an acceleration, get the force, and then divide it by the mass. Okay, it's simple. It's kinematics, or sorry, it's dynamics at this point from Physics 20, where we've got the force, we just divide it by mass to get the acceleration. The trick here is in Physics 30, you've got to find the force in some other way, like using the electric force equation or the magnetic force equation that we haven't learned yet, or whatever other force we might be talking about. Joel?
The way I read this question,
It is? Okay. How did you read it?
well, I don't know what I did here, but I got all three charges all balanced out. Or actually the one that matters between the first and the second, I got 8 over 3.
8 over 3.
Because the way I read it, they all touch, and then whatever separates them.
Okay. Okay. I see what you're saying there, but you did read it wrong. It says the 2 Coulomb charge is touched with the second charge, and then it's touched with the neutral object. So it's the 2 Coulomb charge that's touched with the neutral object. Now, if both of those were touched with the neutral object, then all 3 of them would balance out, and then we would divide it by 3. So it would be 2 plus 6 divided by 3. Right? But it's saying the charge is touched with this one, and then it's the first one is touched with the neutral Coulomb, or the 0 Coulomb one. That make sense, Joe? Okay.
Yeah, I read it the same way. And the second sentence, it says, first charge is then separated from the second charge after the touch.
Oh, okay. Yeah, I see what you're saying there. Yeah. Yeah. Okay. Yeah, I see what you're saying there. So the wording of it isn't great. Yeah. Yeah. That's fair enough. If that was a quiz, you'd probably have an argument on that for sure. Is that what you were going to say, Matt, too? Okay. All right. On the second worksheet, we had question number 1. In fact, I don't even think we need to, be honest, do question 1A, B, C, and D. I think if we do 1 or 2 of these, question 1 and A and B, or 1A and C or something, I think we're probably going to be fine. What we don't do, I'll ask you to try yourself again, after we've gone over a couple things, and make sure you're okay with it. If you're not, then ask me about it again. All right, worksheet number 7. Let's take a look at 1A. We've got 3 charges in a straight row. The first charge is 2.5 times 10 to the minus 2. The second one is negative 4.00 times 10 to the minus 2. And the third one, the second one is 60 millimeters. We're given that distance there, so let's write that down. 60 millimeters to the right of charge number 1. The third one is 3.00 times 10 to the minus 2. I guess I'm looking at 2. Yeah, I guess I'm looking at 2. Let's do number 2 since I've got that picture drawn. Is that okay? Is it okay if we do number 2 instead of number 1? It's the same thing, right? Just since I've got the picture drawn. And the third charge is 5 centimeters. 5 centimeters to the right of charge 2. We got a couple ugly things here with units. First of all, the fact that it's not meters. Second of all, the fact that it's different units. It's different, not meters. 60 millimeters converts to meters by dividing by 1,000. It's going to be 0.0600 meters. 5 centimeters divided by 100, so it's going to be 0.0500 meters. Now, we want to find the net force on the first charge, on charge number 1, due to charge 3 and charge 2. Let's pretend 3 isn't there. Let's look at charge 2 and charge 1 only. Charge 1 is positive, charge 2 is negative. Are those going to attract each other or repel each other? They're going to attract each other. Good. That means if 2 is attracted to number 1, 2 is going to be pulled to the left. We're going to call that the force of 1. 2 is going to be pulled to the left, but really we don't really care, right? Because we're looking for the net force on which one? On number 1 here. So the force acting on number 1 is going to be to the right. The force of 2 on 1 is to the right because 1 is pulled to the right as it's attracted toward number 2. Now the force of 3 on 1, let's pretend 2 isn't there now. The force of 3 on 1 acts which way? Attractive or repulsive? 3 on 1. It's repulsive because they're both like charges. They're both positive charges. 3 is going to repel 1. 3 is going to be pushing away number 1. If it's pushing away number 1, it's going to be pushing it to the left. So the force of 3 on 1 is to the left. Let's get the values of both of those forces now. The force of 2 on 1, or at least the magnitude of the force of 2 on 1, is kq1 q2 over r squared. That's going to be 8.99 times 10 to the 9, Coulomb's constant, times q1, 2.50 times 10 to the minus 2 coulombs, times q2, which is 4 times 4.00 times 10 to the minus 2 coulombs, divided by 0.0600 meters. Be careful here again. Don't forget to square it, and don't forget to use meters. We do the math on that one, it works out to be 2.4972 times 10 to the 9 newtons. So it's a big force, really big force. Now let's get the force of 3 on 1. This is the trickier of the two, I think. The force of 3 on 1. It's kq1 q3 over r squared. What's the distance there that separates 1 and 3? What distance do we use here? Ashton? The combined, which is 0.11 meters, right? We can't just use 0.0500 meters because that's the number that was given to us, right? That's not the number that we want here. We want the distance between 1 and 3. We've got to do a little bit of addition to find that number. When we do the math on that one, it works out to be 5.5723 times 10 to the 8 newtons. Now we go to combine those forces. The net force is equal to F2 plus the force of 3 on 1. What do we got to be careful of when we're adding these two up? Jade? Yeah, the positive and negative thing, right? Is it force to the left or a force to the right? F2 is a positive value because it's to the right. So we're going to say positive 2.4972 times 10 to the 9 newtons, plus the force of 3.1, which we're going to call a negative value because it's acting to the left. So it's going to be negative 5.5723 times 10 to the 8 newtons. And when we do the math on that one, it works out to be 1.94 times 10 to the 9. Does that make some sense, you guys? Do we need to go over a question B or a C? I want to go over question D for sure. But do we need to go over a B or a C? It's more of the same thing, but if we need more practice on the same thing, then we'll do that. Yes, no? All right, 2 people I see nodding no, so nobody's nodding yes, so we'll say no. Try them again. Again, if you struggled with question 1 and 2 on this worksheet, try them again after we've gone over this. If you're still struggling with it, then make sure you ask me. This is what your quiz is on tomorrow, right? Stuff that we just did. So if you're struggling with it, I'll find out tomorrow. It's better just to tell me today and we can go over it, okay? All right, question D for worksheet number 7 says, if the first charge has a mass of 25 grams, 25.0 grams, which is the same as 0.0250 kilograms, because we divide by 1,000, then we want to find the acceleration. We want to find the acceleration given the force that we just calculated, which was 1.94 times 10 to the 9. How did I just say a few minutes ago that we calculate the acceleration of a charged particle? How do we calculate the acceleration of anything in physics 30? First of all, find a force, and then do what with it? Divide it by mass, right? So let's do that for this question. The acceleration is the force over the mass. We've already got the force because we already calculated it in question A. Had we not found it in question A, then we'd find it, and then we'd divide it by the mass. So it's going to be 1.94 times 10 to the 9. And divided by the mass of 0.0250 kilograms. We do the math on that one. It works out to be 7.76 times 10 to the 10. Now we can use newtons per kilogram, or we could use meters per second squared. That's a big number. You guys may have learned in Science 9, when you were doing the heat unit, that the fastest speed that anything can travel is the speed of light, which is 3.00 times 10 to the 8 meters per second. So is there a problem with this? If the fastest speed that anything can go is 3 times 10 to the 8 meters per second, must this be incorrect? There's no reason why this one has to be wrong. If you get a speed that's bigger than 3 times 10 to the 8, you're wrong. Try it again. But there's no reason why this one has to be wrong based on the value of it. What if we just calculated? The acceleration, not the speed. All we know in this question is that it accelerates to a speed approaching the speed of light really, really quickly, in less than 1 second. Okay, there's no upper limit to acceleration. There is to speed, but there's no upper limit to the value of the acceleration. Why would the acceleration be so big here? Just a quick answer, quick qualitative answer. Why do we get such a big acceleration here? We're dealing with a force that's fairly big, pretty big, 1.94 times 10 to the 9 newtons, and we're dealing with a mass that is small. If you're dealing with a big force and a small mass, what are you going to get for an acceleration? Big value, right? You okay with these homework questions? Again, make sure that you're not having any trouble now with question 1 and 2 on this page. Try them again. Ask me tomorrow, okay? I'll even go over another one tomorrow if it's from this worksheet before the quiz, if it's from this worksheet because you've tried it again and you still had trouble with it, okay? Or come and see me after school or lunchtime or whatever. Good. Colin?